is equal to twice what he bet, and if he loses, he simply loses the money that he bet. So the decision is how much should he bet? Because he starts with an amount of money or available money which is equal to B, and the decision is quanto scommette, how much money should he bet. First of all, let's see one thing, that the probability to win is 0.6. So definitely, if you use your wisdom, this is a game where it's convenient to bet. Because if you compute your expected outcome, this would be 0.6 probability to win times the amount of money that he wins, 2D, plus 0.4, which is the probability to lose, times 0. This is equal to 1.2 D. This is the expected outcome of any bet. Okay, so if basically you decided to adopt the second option I mentioned before, a safe value, what would you do? You wouldn't bet, because if you want to be safe, you wouldn't bet anything, because you have the risk of losing money with a probability of 0.4, which is less than half, but still insignificant. So if you want to be safe, you should say, no, please, I don't bet. Thank you. I take my money, I keep my money B, and I don't bet. This is the safe solution, but it wouldn't be a wise solution, because the probability to win and also the expected value of your amount of money that you win is higher than what you bet. So it wouldn't be a wise solution to say, no, I don't bet. On the other hand, if you adopted the first option, I want to maximize the expected value of the amount of money that I can win, you should, anytime that you bet, you should always bet all the money that you have. Because if you want to maximize the expected value, again, of the money that you win, then if you have an amount B available, you should bet all this amount, and then if you win, you should try again and bet again all the money, which would be clearly unreasonable, because it's almost impossible, if you bet many times, that you end up winning, because of course you have a probability of 0.4 to lose, and therefore if you anytime you bet and you think about betting 10 times, it's impossible that for 10 times you win. Almost impossible, not impossible, because with probability nothing is impossible. But of course it wouldn't be a wise solution every time to bet all the money. The wise solution would be anytime I bet a percentage of my amount, for instance half. So the first time I just try with half B, and then if I win, I again with half, or maybe 1/3, or maybe 2/3, depending on your propension or adversity to take the risk. You may decide even anytime to bet 80% of your amount of money if you are willing to take the risk and you want to maximize as much as possible the amount of money that you win. But it wouldn't be definitely a wise solution not to bet and to bet all the money. You just have to find a midway. So I would try this bet, but not with all the money. I am a prudent person, so I probably would try with 20%. So it's not a big deal if I lose. But this is a personal opinion. So the moral of the story is that we should find a way to take the best decision by considering our individual aversion or propension to risk. So, if I am a person that likes the risk, of course the decision will be different with respect to the decision that is taken by a prudent person, and therefore we have to be able to introduce the evaluation of the adversity and propension to risk. This is what happens if you have uncertainty that comes in. Okay, at this point I can open the PowerPoint. The first slide is just say what I mentioned so far. So there is the gambler paradox, and this is again the gambler paradox, and then let's start considering methods for evaluating the risk so as to be able to take the best decision depending on our adversity or propension to risk. And one first method is called sensitivity analysis. It's very simple. I will give you an example of sensitivity analysis, and it's a bit boring, the example, because it involves some computation, but still I think it's instructive, and as you will know, sensitivity analysis is very, very simple. What does it mean, sensitivity analysis in practice? And then we will look at the example. It means that you try to see what happens if you change the parameters of the objective function. They are defined with uncertainty, so the question is, what if I make a wrong assumption? I use exact values instead of uncertain values. What if, for instance, I use expected values? What happens if I make a mistake, if the reality is not equal to the expected values, but is something different? So I look at the money that I lose if uncertainty comes into play and the values of the parameters of the objective function, for instance this one, are not those that I used to identify the best solution. So I have this objective function, I will assign values to the parameters, and I will inspect what happens if these values in reality are different. Here, this objective function, the first part is the same objective function that you considered before for the Lagrange multipliers, for instance, and there is a cost term that is added at the end. This is a cost term because it's negative. You see that x is your water allocation. For increasing allocation, you have this negative term that is increasing. So this means that this objective function does not have an asymptotical maximum value, but has a well-defined maximum. Because for low value of x, the cost is negligible, and therefore you have an increasing benefit for increasing x, but as x increases, then the cost term becomes more influent, and at a certain point, the subjective function starts to decrease for increasing values of x. Now let me consider these values for the parameters. These I changed with respect to the slides that were online until this morning, so this is an important thing that I changed. So if you assume that A is equal to 60, B is 0.08, C equal 1, and D is 0.7, we get this type of objective function that has an optimal value for x around 38. Now, just 5 minutes, I want to show you how simple it is to identify the best value for the subjective function. And we can't use Lagrange multipliers for this, because the presence of the cost term makes the computation of the derivative not possible analytically, and therefore we can't use the method of Lagrange multipliers. So we have to go with the simulation procedure. I mentioned to you last week that simulation or numerical solution are an alternative to the analytical solution. And I mentioned to you that it's very simple. Basically, one has to try several values of x and then keep the one by chance, just by chance, but just by trial and error, and then keep the one that gives the maximum benefit. And I want to show you now, very simply, in 5 minutes, how this can be done in R. So, let me please write down the subjective function and write down also the value of the parameters. So A equal to 60, if I well remember, let me see, yes. B 0.08, C 1, and D 0.7. And let's try to find the maximum. Now let me open R window. Let me try to increase font size, okay. And basically, first of all, I have to write down the benefit, the function, the net benefit function. So is MB equal function of x. And let me compute then the objective function, which was 60 times 1 minus exp 0.08 times x minus 1 times x to the power of 0.7. This should be the function. Let's see what happens with some trial values. MB10. Oh, sorry, I forgot to give the instruction to return the result, so I go back. Return PR1. Okay. And now let me try MB10. Should work now. No, it's negative, so there is something that is wrong. Okay. This was minus, correct? Fine. MB10. Okay, this is reasonable. MB20, 39, MB30, 43, MB50, 43 again, MB60, 41. So you see that there is a maximum between 30 and 50. We could identify the maximum by keeping trying, but this is not very much convenient. It's more convenient to write now a routine to find the maximum, a numerical routine. The numerical routine indeed is very simple. Let's suppose that we have already identified that the maximum is between 30 and 50. So let's say that the maximum is for sure, if we want to be safe and consider a wider interval, let's say that the maximum is between 1 and 100. This is a kind of prior information that we gained by making some trials, which is very important. When you look for solution to an optimization problem, any prior information is very much important because it allows you to reduce the number of trials. You will see what I mean in a moment. So first of all, let's define the variable of allocation and the variable of max fun, which are the maximum of the function, of the objective function, and the corresponding allocation. So now what I need is just a full cycle which I can repeat like 10,000 times. Usually you don't have any problem here. 10,000 means many times. You have to repeat many times the trials. Now let's put a parenthesis, and now we have to generate. So let me generate here one equal a random variable which is uniformly distributed. Runif, you see the instruction. One random variable uniformly distributed from 1 to 100. This instruction generates a random outcome, one random outcome, which is the first argument of the function, between the two extremes of 1 and 100. Okay, in this way we generate this random variable. At this point we have to compute the corresponding benefit, and then we have to evaluate whether the benefit is the highest one that we found so far or not. And therefore let me put a if, and then we say if PR2 is greater than max fun, then another parenthesis, we have to say max fun equal PR2, which means that if I found a greater value, I keep it, and then I also have to keep the allocation equal to PR1. At this point, I can close the first parenthesis. I would say that I can close also the second, and then I press the enter, and you see that it was very quick. Now let me see, allocation is 37.67 and the maximum is 44 of the directive function. Let's go back to the graph that I showed you before. You see, I found 44 and the allocation was very easy, just by trying, by chance. Of course, if I increased the value, I changed the number of iterations, the precision of the solution changes as well. So let me see what happens if, for instance, I make just 10 trials. It's quite obvious to think that, to argue that probably the result is not as correct as before. Let's just try. So here I can just try 10 times. There is the problem that I have to put equal 0 and max fun equal 0, fine. And now let me go back to 10 times iteration, 10 iterations, and then everything is unchanged. Okay. Oh, I forgot the parentheses, I'm sorry. I start from the beginning. Okay, and then the parentheses, and then okay, and then I have the net benefit to compute. Here I am, then okay. 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 So let's see what happened here. I just performed 10 iterations. Allocation is 51. Max fun is 43. So you see that it's not as correct with just 10 iterations. of course, if you reduce the number of iterations, it would be advisable to reduce also the range in which you try. And then, if you reduce the range, then you can reduce the number of iterations. Another very useful prior information would be the probability distribution of the allocation, because I use the uniform, which means that it looks in the whole interval with equal probability. If I use the Gaussian distribution, for instance, it would concentrate the trials around the expected value of the Gaussian, which would be convenient if we had a prior information like the one that I gained with the few trials that I made before. I understood that the maximum was between 30 and 50. I could have given a Gaussian distribution with average on 40 and proper standard deviation to well cover the interval between 30 and 50. Okay, this was just an example to show you that the numerical solution very often is convenient, and also to show you that it's very easy to find this graph. In this case, I kept all the trials, and therefore I was able to draw a curve. But in any case, it's very simple once that you have assigned the parameters to find the best decision, the decision that maximizes your benefit. But there is to say that in this case, I assume that the parameters were exactly given. So what if the parameters actually assume different values? This is the scope of the sensitivity analysis. The question is, what if the parameters assume, in reality, different values? So, the sensitivity analysis is very simple. You make different attempts by varying, anytime, one parameter. And then you repeat the estimation of the best allocation and the benefit that you gain. So, if you don't perturb any parameter, you see, perturb the parameter none, then this means that the best allocation, as we have seen, is close to 38. So let's stick on the integer values, because we don't need to look at the digits. So let's say that it's 38 with this benefit. Now let's see what happens if we assume that A is 25% higher. If I increase 25% the value of A, I get an optimal allocation, which is 41, with a benefit that is significantly increased, because A is much effective on the final value of the benefit. And then let's see what happens if I decrease A 25%. And then the allocation, the optimal allocation, becomes 34 with a benefit of 30. You may ask me, how did you determine the percentage of perturbation? This is to be decided based on your perception and your prior information. For instance, do you know the probability distribution of the parameter A or not? If you know it, then you have an idea for an assigned level of probability of the values that A can take. So you may know, for instance, that you perturb A of 25% higher and lower, you cover 90% of the cases. I'm just guessing. So if you know the probability distribution, you have an information that allows you to estimate how much you should perturb. If you don't have this information, you may have other informations to decide how much to perturb. Of course, this is a decision that must be taken depending on the information that you have. If you are not sure, of course, to be safe, you should adopt quite significantly high value of perturbation, significant perturbations. And then you can perturb all the other parameters. So let's go to B. Let's increase B of 25%. And just note that you can adopt different perturbations for different parameters. In this case, to make it simple, it was decided to perturb 25% all the parameters. And perturbation doesn't need to be symmetric. You can perturb 25% higher and 10% lower. It just depends on the case study and the information that you have. But anyway, if you perturb all the parameters, you get a set of cases that allows you to understand what is the parameter that is more effective on the decision. For instance, look at A. A is very much effective on the benefit. You see, this is the benefit that we obtain without any perturbation. If you perturb A, you have a significant increase, more than 20%, I would say 30%, more than 30% of the benefit, and a significant decrease, about 30%. If instead you perturb B, you see that the change in benefit is not that high. But conversely, if you look at the allocation, you say that A is not much influent on the allocation, because against an allocation of 38, we get allocation of 41 and 34 by changing A, which means that A is very much effective on the benefit, but not that much effective on the allocation. But if you look at B instead, you see that on the allocation is more impacting. It's not impacting, let me see, is 32 and 46. Yeah, I would say that in this case is similar. But let me see if I have a parameter that doesn't impact much on the allocation. I would say that C is, yeah, C is not much impacting on the allocation. Therefore, you may check with this procedure what is the parameter that impacts much on the value you are interested in. For instance, if you are very much interested in taking a good decision and you don't care much about the benefit, then you see that A, okay, is impacting, but not that much. Instead, if you look at B, is impacting more, because you see A is impacting from. Okay, in any case, if instead you are interested in the benefit, then you have different situations. Why this information is important? Because if you want to reduce uncertainty, when it is possible, you have to spend money. Because very often you need more data. You need to collect more information. This means money. So you should collect more information if it's really needed, if it is convenient, and you have to know what is the parameter that deserves more information in order to concentrate your resources on the minimization of the uncertainty of A instead of B, for instance. So this kind of information is very useful, which is given by a very simple analysis, you see. It's a very simple analysis that you can carry on. You can derive this table by yourself very quickly, because you have seen that I was able to solve the minimization problem, the maximization problem very quickly. Okay, now, there are some indexes that we can compute to evaluate the results of the sensitivity analysis. So let me quickly go through this point. And because, of course, in order to perform a clear evaluation, a transparent evaluation, it's better to compute some indexes, not just looking as I have done, because you have seen that while I was commenting the table, I tried to get an overall picture, but it was not really easy because you have to look at many numbers. So instead, if you try to synthesize the results through indexes, this is helpful. So let me define now some symbols, and let me indicate with the symbol net benefit MB X star W the maximum benefit with an optimal decision and the correct parameters. So let's suppose that this is our first row of the table that I've just shown to you. So this is the benefit that I take when the parameters are correct and the decision is optimal. Now let's suppose that the parameters are wrong. Then if the parameters are wrong, you take a wrong decision. Let me indicate with the symbol MB X prime W prime the benefit with the wrong decision and wrong parameters. This means that if your parameter values are perturbed, then you get wrong parameters, you get a wrong decision, and then with the wrong parameters you can compute the benefit given by the wrong decision. But there is one other information that you can collect, which is the benefit that you take with the wrong decision and correct parameters, which is important also to know. So once that you have taken a wrong decision, let's see what is the benefit that you obtain with the correct parameters. And let's indicate it with the symbol NB X prime W. Okay, now, given these symbols, so remember just for clarity that the prime identifies wrong, okay? Now let's introduce here, let's complete the table. So for each perturbation, I have the optimal decision, which is wrong decision in these cases, because when I perturb I get a wrong decision, and then I can compute the benefit with the wrong decision and wrong parameters, and the benefit with the wrong decision but correct parameters. So the difference between these two columns is that here I computed the benefit by using the perturbed parameters anytime. Here I compute the benefit by using the unperturbed parameters. And just note that in the first case, in which I have no perturbation, the benefit that I'm computing, which is without perturbation, so correct parameter and then correct decision, is just equal to the benefit with the correct decision and correct parameters. So it's NB X star W that I indicated before. Okay? And then I can just move forward to compute these indexes. And let's try to understand why they are important. Please pay attention, because these are indexes that basically synthesize the sensitivity analysis, so it's quite important that you try to learn them by memory. And please note, in order to help you, that the denominator is always the same, which is benefit with correct decision and correct parameters. So the denominator is always the same. What changes is the numerator. And in the first case, you have an index that quantifies your loss in economic efficiency. What does it mean? You take a wrong decision, and therefore you have a wrong benefit. Let's see how much you lose. In fact, you see that here, apart from the index, the multiplier 100, which is everywhere. So this is another common behavior of these three indexes. At the numerator, you see that we have the difference between the optimal benefit with correct decision and correct parameters minus the benefit that you take with the wrong decision but correct parameters. And for sure, this benefit here is lower than this one, NB X star. Is lower because X star is the optimal decision, so any other decision, including the wrong one, is giving to you a lower benefit if you don't change the parameter values, if you keep using the correct parameters. So this index here is positive for sure, which means that if you perturb the parameter, for sure you have a loss in economic efficiency. But then, this is not the only one feature that it's convenient to evaluate. The second index estimates the error that you make in the estimation of the max benefit, meaning that if you use the correct parameter with the correct decision, you would estimate a benefit NB X star W, but indeed, when you perturb the parameters, you estimate a different benefit, which is the benefit that you estimate with the wrong decision and wrong parameters. So you make a mistake. You estimate a benefit which is not the one that you would take if you didn't perturb and you used the optimal decision. So this one here is the maximum benefit that you can take. Here, it's what you estimate. And this can be, index can be positive or negative, because when you adopt the wrong parameters, you can overestimate your benefit. But what happens actually? What happens in reality? In reality, what happens is that you get a benefit which is not the maximum possible one. It's a benefit that is given by the wrong decision with the correct parameters. This is what happens in reality. But you don't estimate with the wrong parameters this benefit. With the wrong parameters you estimate the benefit x prime w prime. So this index is useful because it tells you what is your error in the estimation of the real benefit. This index tells you the error in the estimation of the maximum benefit. This index is important because it tells you your estimation error of the real benefit. And I would say that we can stop here, but just let me check. Okay, this is just a table where the value of the indexes are reported here. And you see that it's interesting because depending on what you are interested in, this table tells you what are the most effective parameters and the consequences of a wrong decision. Let me just check. Okay, fine. One final thing. Let me stop the camera.